Hello, in this video we are doing a multiple regression example using JASP. So we are using the Regression Practice 1 dataset, which is the exact same dataset we used for the linear regression example. So we've got these same crime statistic variables for 50 US cities. The difference is that we are doing a multiple regression, so instead of just having two variables, one predictor and one response variable, one dependent variable, this time we have three predictor variables and one dependent variable. So three independent variables, three predictor variables, and this one dependent response variable. So our research question is, does x3, x5, and x6 have a significant influence on x1? And remember, when you see influence, think prediction. And so what we're asking here is if annual police funding, percentage of 16 to 19-year-olds not in high school and not high school graduates, and percentage of 18 to 24-year-olds in college has a significant influence on the total overall reported crime rate per 1 million residents. So that's what our research question is. In terms of what statistical test and why, a multiple regression should be used because it helps to predict, which remember I said if you see influence, think predict, the results of one dependent outcome variable, that's our one dependent outcome variable, on multiple other independent predictor variables. So here are our multiple independent predictor variables. Like a linear regression, the variables are numeric and linked by a common categorical variable. In this example, it is city. The main difference between a linear regression and a multiple regression is that a multiple regression has more than one independent predictor variable. For our hypotheses, we've got our null is that there is no significant prediction of total overall reported crime rate by annual police funding, percentage of 16 to 19-year-olds not in high school and not high school graduates, and percentage of 18 to 24-year-olds in college. And then our alternative is that there is a significant prediction of those things. Now, to run the test in JASP, if you are doing this for an assignment and you have to, like, you're creating the data, so maybe for assignment 4 or assignment for week 7 assignment, you need to make sure the data is organized correctly in Excel, save it as a CSV file, so that way it will open in JASP. But for us, we already have the data file, so we just need to get it open. So let's go ahead and open JASP. So we've got JASP open. We're going to go up here, go to open. For me, it's a recent file because I just got done doing the linear regression one. But if you haven't, then make sure to go to your computer where you have this file saved and open it up. But for me, I can just come over here and then go ahead and open this. So remember, we're using x1 as our outcome dependent variable. Then we're using, what is it, x3, 5, and 6. These are all numeric scale variables. So we are good to go there. You can see these are all numeric scale. And what we're going to do is come over to regression and classical and linear regression. So regression, classical, and linear regression. This is going to seem super familiar and very similar to what we did for the linear regression. So go ahead and click on that. And similar once again to that linear regression, our dependent variable, that outcome variable, right? We only have one of those. In this case, it is x1. That's the outcome variable, that dependent variable. But then in terms of our predictors, our independent variables, those covariates, we have more than one. And this is what makes the difference, or this is why it's different from a linear regression. So this time we are doing 3 and 5 and 6 right there, right like that. Then under statistics, we need that Durbin-Watson. So what yours needs to look like, you want to have all of those predictor variables listed under the covariates. You've got that dependent response variable in your dependent variable box. And then under statistics, make sure to check the Durbin-Watson box. You need to have display model fit, and under coefficients estimates. But otherwise, you should have all then of your correct information. Now, if you're doing that screenshot for the quiz or the screenshot for an assignment, this is all of the information. So you need to make sure you screenshot all of this information. In terms of what information you're looking at, for Durbin-Watson, for the M1, that Model 1, you're looking at that 1.407. So that's the number you're looking at for the Durbin-Watson. You want it between 1 and 3. You're also looking at the adjusted R-squared, and this is super, super important. For a multiple regression, it is the adjusted R-squared, and the reason it's the adjusted R-squared is that it is adjusted for the fact that you have more than one predictor. If you only have one predictor, like a linear regression, you use R-squared. But for a multiple regression, it does not make sense to use the R-squared value. So big X on R-squared, and we are only using the adjusted R-squared value. And then for the ANOVA, what we're going to be looking at, once again, similar to the linear regression, is the degrees of freedom are going to be that regression and residual, so 3 and 46. We've got our F value of 7.174, and then we've got this p-value that is less than 0.001. So we do have a significant p-value, which means we are rejecting our null. Yay! And then for the coefficients, we are going to be putting together the regression formula, and that's going to use that Model 1 intercept, and then x3, x5, and x6 unstandardized coefficient value. So those are the values that we're looking at. Let's go ahead and go back to the worksheet and see how all of this fits together. So for how to interpret Durbin-Watson, just like I said, just like with that linear regression, it checks for correlations between the residuals, which is the difference between observed and expected outcome variable, and the value should be above 1 and below 3. So we've got this 1.407. So yay, we got a good value there. How to interpret... I wonder why that is not all the way over. Sorry. How to interpret the adjusted R-squared value. Remember that adjusted R-squared value lets us know how much variation of the outcome, that dependent variable, is explained by the independent predictor variables in a multiple regression model. It's also a measure of how close the data are to the fitted regression line. For a multiple regression, the adjusted R-squared value is used instead of R-squared because we need to adjust for multiple independent predictor variables. To report this value, just multiply it by 100 to get that percentage. So our adjusted R-squared is 0.274, which you can see falls into that fair fit strength. And over here, you would just say a fair amount, 27.4%, of the variance in total crime rate is explained by the 3 predictor variables. Now, normally you'd go ahead and say what they were, but I was kind of running out of space there. And to get that 27.4, you just do the 0.274 times 100. Then determining degrees of freedom. Just like I mentioned before when we were in JASP, you're looking at the M1 model, and it's the 3 and the 46, so the regression and the residual, and it will look like that. How to interpret the p-value. P is less than or equal to 0.05, we reject the null, and if it's greater, we fail to reject the null. So in this case, our results are significant, and we need to reject the null, which is super important. Make sure you always include that information in any and all write-ups. For the multiple regression statistical results, this is what it should look like. So remember, italicize those important statistical letters and no leading zeros. So that is how you go through and work through the main information. But let's go ahead and take a look at how to determine the multiple regression formula. So very similar, and I know it's like I keep saying very similar, but it really is really similar to the linear regression. We're just adding a couple extra coefficients, a couple extra variables. And so that multiple regression formula provides a way to estimate what the outcome variable would be given specific predictor variables. This model uses the M1 intercept and regression coefficients. So we've got that y hat. And so if you think about it, this is like that y equals mx plus b. So you remember, line and best fit a line and that type of thing, or the, equation of a line, y equals mx plus b. Very, very similar. So we've got our y hat, which is what we're predicting. In this case, our y hat is just that total overall reported crime rate. And then we're adding our intercept. And the intercept is just kind of, well, first of all, it's that 79.303. But what it is, it's the kind of the value that we need to offset the values for the coefficients in order to make the model work. In this case, that intercept is that 79.303, which you can see here in this formula. And then I'll scroll down a little bit. We've got plus coefficient x3, which is the police funding, times an x3 value. So that would be an actual, what x3 value someone has. Then percent of 16 to 19-year-olds not in high school and not high school graduates, our x5, and then our percent of 18 to 24-year-olds in college. And where, for example, these are coming from is in here for JASP. Let's go back to JASP. And right here. So where you would, and remember, and I know I had said this for the linear regression. So first of all, you do need to come up with the multiple regression formula. So you will be required to know how to put together the multiple regression formula. These examples, you do not need to replicate. You will not need to do this for any quiz. You will not need to do this for any assignment. I am purely doing this because we are academics. We all love learning and we love statistics, or at least I do. And I want you to just be kind of better informed in terms of understanding what does this regression equation actually mean, right? So in this case, what we would do is take that very first, let's do Kiwani, and our x3 value is 40, our x5 value is 11, and our x6 value is 31. So we take those values and we just plug them into the equation to get what we would expect. So, right, so this is the expected total overall reported crime rate, right? So this is what we expect. So we would think for that town, they should have a crime rate of 692.2, given, right, the 40, the 11, and 31 for our, entered into our model. Because remember, this is our best fit model. This is what we think is going to happen. And given what we think what's going to happen, we expect this value to be that outcome value. Now, if we look over here at our actual X1 value, we see that's only 478. Now, I'm going to go into, in class, we're going to actually talk about outcomes and residuals and things like that. But you really want this X1 variable, or this number, to be a lot closer to this number. Because the closer they are, the better fit the model. In this case, it's not a great fit. But remember, you never have to do this for class, anything like that. Or we are doing this for class, but you never have to do this for any assignment. Now for the next example, in this one, we are looking at 25 in annual funding, 8% of 16 to 19-year-olds, and 32% of 18 to 24-year-olds. And you can see where those numbers came from. Let's see, X3, there's 25, 8, and the 32. And so what we're looking at is 603. So we think it'll be 603. So that's what not only we think. So this is actually what it really is. Let's look and see what we would expect it to be. So put it into our nifty little equation and we get 503. So we would expect it to be at 503.3. That would be our expected reported total overall crime rate. But you can see what we actually had, and that was what Gibson City was, 603. So pretty good difference. And as I've talked about before, that difference between what we expect and what we see, that's residuals. And the bigger that difference is, kind of the more off the model is, you will have a less significant model and you will have a smaller adjusted R-squared value. So if you remember, our adjusted R-squared value wasn't that great, right? It was only 27.4%, right up here, only fair. And that likely has to do with we are seeing some pretty good difference between what we expect and what we actually had. So that is how you interpret the multiple regression formula. Remember, for quizzes and assignments, you do not have to actually, do an example interpretation. I just wanted you to understand what, the regression equation meant But you do need to do the equation, so you do have to actually come up with this. You just don't have to use any examples. So let's go ahead and take a look at the written results. So for the written results, we have that a multiple regression was calculated to predict total overall reported crime rate based on, and then all of our predictors. Our null is that there is no significant prediction, and our alternative is that there is a significant prediction. The Durbin-Watson value was normal, indicating a valid test, and a significant regression equation was found. And the null hypothesis was rejected. So very important, you need to make sure you're saying you have a significant regression equation. If it's not significant, then very important to say that it's not significant. And you need to make sure to say that the null hypothesis was rejected or that you fail to reject the null hypothesis. So those are two really super important parts right there. The next is that F value. Make sure to italicize the F and the P and that adjusted R squared. Then we've got those degrees of freedom, our F value, our P value, and the adjusted R squared value. We then interpret that adjusted R squared value by saying this means that a fair amount, that 27.4% of the variance in crime rate, can be explained by annual police funding, and kind of then explain those are all of those predictor variables right there. And then last, and so this is all, so you're like, whoa. So this is kind of a longer write-up than some of the ones that we did in week 1 and then for the week 2 quiz. But you would then say the regression equation for predicting total overall reported crime rate from annual police funding, percent of 16 to 19-year-olds not in high school and not high school graduates, and the percentage of 18 to 24-year-olds in college is, then you would give that regression equation. The results indicate that annual police funding percentage of 16 to 19-year-olds and the percentage of 18 to 24-year-olds can be used to predict overall reported crime rate. Yet the predictor variables only account for a fair amount of the variance in overall reported crime rate, so it's likely that many other variables impact this variable. So there is your example written results. I hope this helps, and if you have any questions, let me know. Also, if you want additional examples, we will be going through 2 additional examples in our live class session. So make sure to either attend that live class session or make sure to watch the recording, because we will have 2 additional examples for the multiple regression in that live class session.